Mike's here.
How's it going?
Good here.
Hey, Carter, this is John.
Hey, John, good to see you.
Hey, good to see you as well. Hey, thanks for setting this up. Are you going to kick us off, or do you want me to just get started here in the next couple of minutes?
Yeah, I'll do a little introduction and then hand it over to you. We'll give it just a couple more minutes, though. I think there are a few more people joining.
Perfect.
Okay, I'll let you know.
John, do you go by John or Yon?
Okay, John, well, I think we can get started then. Well, thank you for doing this. For everyone just logging in, so this is Jon Gunnerson. He is the geothermal manager for the City of Boise. Him and I met in June. I had the opportunity to take a tour from him and see all of the Boise's district heating system. And I think it looks like we're gonna get a really similar presentation to what I got that day, which I think is going to be really useful for our theme that we have. John, maybe to fill you in too, we've been doing these meetings from people using geothermal around the world in different uses. We had an American who talked about his work in California and Japan. We've had some presenters talk about their work in places like Colombia. And so now we get to hear about your situation here in Boise. So I'll turn it over to you now, John. Thanks again for doing this for us.
Hey, thanks, Carter. Thanks for including me. So I'm going to just kind of jump into talking about what our geothermal program is and what it does and where we're going with it. This is a similar presentation I've given in the past. It's a very high level. So I'm going to just kind of start here, and then we'll see where discussion takes us. And we can drill in any other topics that you're interested in or anything specifically that you want to be learning about. So again, thank you. My name's Jon Gunnerson. I work for the City of Boise. I work in our Public Works Department. I do see that I got another participant here from the City of Boise, Mike Long, who is our operator for the geothermal program. So some technical questions may get routed his way. I've been doing this for about 14 years. I've been managing our geothermal program for about 10 of them. And anyway, we've been making some really big strides in growing and expanding and maximizing the use of this geothermal resource. And that's all stuff we're going to talk about here today. Can everybody see my screen? I don't use Zoom very often. Yep, I'm getting a thumbs up. Okay. So I'm going to start here with a little bit of history on geothermal here in Boise. The world's first geothermal heating district is attributed to be right here in Boise, Idaho. Geothermal has been a big piece of this Boise area for a long time, going back to the 1890s. Basically, what had happened was some of the first Boise developers were trying to seek a contract to deliver water to Boise. And one of the developers had the notion to let's deliver both hot and cold water. This was the Boise Artesian Hot and Cold Water Company back in the 1890s. And they tapped the first geothermal hot springs here in Boise. Historically, this hot springs have been used for centuries for Native Americans for different wintering, bathing, cooking operations, until these developers tapped into this hot springs and started piping it downtown. It was almost an immediate success where they had nearly 300 homes connect. Some of the pictures here. This is the C.W. Moore home. This is notably the first home to ever use geothermal water off of a district heating system. And shortly after, the city built what's referred to as the Boise Natatorium. It was a large public swimming pool using this geothermal water directly. Unfortunately, this grand structure ended up burning down and then rotting the rest of it in the 1940s. And so this is no longer standing, but it is something the city's looking at resurrecting here at some point. Besides this first heating district and besides Native Americans using this for centuries, we also have a series of greenhouses here in Boise that use geothermal water directly for year-round food production. This picture in the bottom right corner is the Edwards greenhouse. This greenhouse is still in operation today. They're still using geothermal water. It's a small family-owned business that's very dedicated to using geothermal. So now, fast forwarding almost a century, in the early 1980s, there was a worldwide energy crisis, and there was a lot of geothermal exploration. And knowing that this geothermal resource was here in Boise, and it was successful through this Warm Springs heating district, the city of Boise got into the business. We drilled 3 wells. The state of Idaho got into the business. We have the only state capital here in the United States to be heated by geothermal. There is another small system that serves our veterans hospital. We have a veterans campus here. They serve about 15 buildings, including their hospital, also right here in downtown Boise. And then just kind of keeping that circle expanded, there are dozens of different hot springs resorts within 100 miles of here. There's lots of use of this resource for sidewalk snowmelt, for aquaculture, fish farming. There's even an alligator farm nearby, greenhouses, mushroom drying, timber drying. There's been a lot of uses, then there still are a lot of uses here in the Boise region. But specifically looking at downtown Boise and what we do, I'm showing you a map of downtown Boise, and this green line is the historic Boise Warm Spring system. Again, it's still in operation today. It's serving about 350 residential homes. Then there is this light blue line here in the middle. This is the state of Idaho system, where they pump it and inject it back into the aquifer. They're heating about a dozen buildings, our state capitol and their entire Capitol Mall. A small VA system on the top of the map. And then the large one here is the Boise City's operation. This is notably the largest geothermal district heating system in the country. And right now we're serving just shy of 6.5 million square feet of downtown commercial space. That's a total right now, I believe we're up to 96 buildings that we're heating. This water is primarily used for their space heating. So we see the biggest peaks here, starting about now and lasting through the next 3 or 4 months. But this water is also used for domestic water heating at about 1/3 of them, and sidewalk snow melt at about 6 of them, and then a couple other various use applications. The water that we pump, let me just kind of walk through our operation here. Everywhere that you're seeing a pink line on this map, there's actually 2 pipes. So this is a 2-pipe system where we're pumping the water from one of the 3 production wells. We're piping it to one of the 96 buildings, in which they use heat exchangers, paint and frame heat exchangers typically, to extract heat off of this water. The water that we're pumping out is 177 F, I believe about 81 C. And we have pumping volumes. Again, it varies seasonally. In the winter times, we're peaking at about 2,000 gallons per minute. And in the summertime, when it's just domestic water heating, we're down to 200 to 300 gallons per minute. So then once the water is piped to a building, we collect it through a second set of pipes and we run it to our injection well, where basically every gallon that comes out of this aquifer is a gallon that goes back into it, making our aquifer truly sustainable and long lasting for generations to come. The water that we re-inject is about 120 F, which is still very hot water. It's still water that has lots of potential in it. It can be used for for space heating, for definitely for heat pump buildings, for these other uses, for sidewalk snow melt, for preheating of domestic water. So in areas near our injection well, we are now incentivizing use of this collection water. Basically, our directors coined this a reuse of a renewable resource, where we have this renewable resource here in Boise, and before it's ready to go back down the hole and be disposed of, we're trying to get another use out of it, trying to get more BTUs, more energy pulled off this gallon of water before it's disposed of. Right now, we got about 10 buildings that use this reused water before we inject it. Any questions so far before I keep moving? Okay, I'll keep going. So our original system, it was built out of it was built as a demonstration project in the early 1980s. The materials were unknown at the time, so we used a lot of concrete pipe and unfortunately a lot of different metal fittings. And that has been our Achilles heel of this system is corrosion on these metal fittings. So that's something that we've been aggressively, proactively replacing here over the last really heavy over the last 3 or 4 years, but more so over the last decade, trying to get this metal out of our system, trying to make it more reliable, so we can keep our system downtime to a minimum. Right now, our preferred material, we're really happy. We're using a lot of the high density polyethylene, the HDPE. As of about 5 years ago, HDPE had a maximum temperature of 140 degrees. Now we're seeing blends of the HDPE that can reach temperatures that can support our water. I believe the HDPE specifies that it can go up to 180, maybe 200 F. So we kind of are right on the verge of its performance, but it is a material that is it's easily to procure. It's cheaper. It'll last a lot longer. Anybody who's worked with this HDPE pipe knows that it's virtually indestructible. I mean, this is some really, really solid pipe that gets butt fused together. You don't need to worry about any couplings, any unions or joints of it. And we've been really happy with it. There are some downsides with HDPE or with all plastic pipes, and that is the coefficient of thermal expansion and contraction. That's something that we are monitoring very closely to make sure as this pipe is heating up and cooling down, as buildings cycle on and off, that this thermal expansion and contraction is not pulling away from any valves or from buildings or from any parts of our system. I mentioned, so we got 3 production wells. We're producing 177-degree water. These 3 production wells can max out at about 4,000 gallons per minute. Again, right now we're peaking at about 2,000. So we almost have double the pumping capacity of what we're currently serving. Right now, our water right, so our water here is managed by the state of Idaho, the Department of Water Resources, and we have just recently secured an additional water right to put us up to, this should actually say 385 instead of 375. We have a right to go up to 385 million gallons of water per year. For comparison, this last year for FY21 that just ended in October, we pumped 250 million gallons. So we have room to grow and expand from our pumping capacity. We have room to grow and expand from our water rate capacity. And then we inject all this water, again, at a temperature about 120 F. And our injection also has ample capacity for additional growth and expansion.
Hey, John, I had a question.
Yeah.
And that is, and maybe I misheard you. One time I thought I heard the injection temperature like average 140. Here it says, which would be like 60 degrees C. Here's 115, which is like 46. Are the users limited in terms of the return temperature that they can draw it down to, or are they allowed to go down as low as 110 or something like that if they want to build a exchangers that size?
Yeah, great question. So we encourage the maximum use of this resource. So there is no minimum temperature to return it at. And the average temperature that we're seeing most buildings pull off is about a delta T of 50. And that is just kind of been the standard of what buildings are pulling off. Some buildings can get above that. Some buildings struggle to get a delta T of 50. The buildings that do get that, we have some buildings that can get a delta T of 60, 70, and sometimes even 80 degrees off of this water. And we highly encourage you to pull as many BTUs, as many therms off each gallon of water as you can. Now, what that means typically is their capital investment of what's inside of a building and what size is their heat exchanger. And then the other that we're also seeing a lot more of and that we're encouraging is the cascaded use of this water. So you use it once, you pull off 50 degrees to heat your building, but now this water is still 120 F, and so then they will run it through a second heat exchanger to either preheat their domestic water or run it through a third heat exchanger even and heat their sidewalks for snow melt. So we've got 2 examples of buildings who've been very innovative that have used this gallon of water and ran it through 3 separate heat exchangers to maximize their delta T's, to get as much energy off of this as they can. Because this is a water right, because we're limited on how many gallons we can pull out of the ground and re-inject, we have to bill, we have to set our rates by gallons, by how many gallons the buildings use. We get the question pretty often, can we bill off therms? Can we bill off the energy that's pulled off of it? And unfortunately, we cannot, because I cannot afford for a building to, we'll say hypothetically, run 1 million gallons of water through their building and pull no heat off of it. And in theory, would have a 0 bill if they pulled no heat off that water. But that's still 1 million gallons that that's coming off of a water right. It's still 1 million gallons that we have to pump, we have to inject, we have to manage. So our rates are set by the gallons, with a couple exceptions, but for the most part, we bill it by the gallons, and we encourage the most efficient use of this water as possible. Did that answer your question?
Yeah, great. Thanks. Good stuff.
Hey, John, we've got a question in the chat too. Nick said, are the HDPE suppliers providing a complete pipeline solution in North America, say pre-insulated with leak alarm lines?
We are getting it pre-insulated. We do not have leak alarm lines. We do monitor our flows and our pressures very closely. And so any large leaks that we have in our system, we can identify through our monitoring system. But we also have another couple tools in our toolbox, and I'm going to get to those on our next slide. But yes, the HDPE is being supplied to us here locally. It is being insulated here in the United States. You know, something else that we found that we really enjoy about this product is it's a common material. I mean, this HDPE, whether it be different strains of it, is used in the sewer industry. It's used in the domestic water industry. So most contractors that we use are very familiar with it. They know how to work it. They know how to install it. They know how to weld it, how to pressure test it. And with our water not being extremely hot or at extremely high pressures, it has just seemed to be a very, very good candidate for our program here. Now that is currently our pipe of choice, our material of choice, but we also do still use a lot of fiberglass pipe, and both materials have their applications. So specifically, I guess, so when we're laying pipes here in Boise, most of our system is in a downtown core. And so we're in a very tight area with lots of utilities, lots of impacts. And so when you use the HDPE pipe, often it needs to be welded together, and it's a really big machine that welds it together. And it's hard to get that down into the trenches. So a lot of this needs to be welded up on the surface, and then the pipe pulled down into the trench. And so, as you can see from a couple of these pictures that I'm showing, when we use HDPE, we really have to open up a large area at a time. I mean, this one, I mean, we're showing an entire block, you know, over 300 feet of trench opened at one time. Sometimes we can get away with this. Other times, just being in the heart of a downtown core, this is a prohibitive. So then we go to our other material, which is fiberglass pipe, which is, you know, bell and spigot. Some of it we glue together, some of it we have fiberglass couplings to hold it together. And here we can go stick by stick. And so if we're in a really sensitive area of downtown, we will look at our different material selection and identify what material will be best for this location to minimize impacts to business, to customers, commuters, and everybody alike. So we're currently, the city's currently going through our strategic planning process. Basically, our geothermal program developed in the 1980s. Again, it was built as a demonstration project. Nobody knew how big it was going to get, how successful it was going to get, and so I'm going to say now here, 40 years later, the system is aging. It's also maturing. And so we've decided we need to take a big step back and really put the framework around what our geothermal program should be, could be, where we're going to take it. You know, what do we want to see in the next 100 years with it? And so for a really simple visual, we put this pyramid together, this triangle, where on the bottom we always want to make sure we're taking care of our existing customers. There's a handful of these, of the 96 that we have connected. There's about 40 of these buildings that have been connected and been a customer from day one. And we want to make sure we don't lose sight of that. And so we made sure we put that at the bottom of our pyramid here. Basically, I'm going to call it kind of a foundation. You know, we want to make sure our foundation is solid, that we're taking care of our existing customers, our existing system, and how we operate it, and make sure we really have this solid foundation. We're almost there. Just in these last couple of years, we made significant improvements to all different aspects of how we monitor, how we bill, how we collect information for our program. So we're now kind of moving up to this next tier, and that's now we're looking at growth of the system. Growth of the system comes on many different layers. I'm going to flip back to our map really quick. One growth that we're targeting really aggressively is infill of our system. We have a lot of pipeline. We have about 21 miles of pipeline in our system. And as you can see from the map, a lot of these customers, a lot of the buildings that are connected are spaced apart. And so there's a lot of potential to infill and get buildings connected that are already adjacent to our system. So right now we have some discounted rates. We have some incentives where they'll get a couple years free water. We've got some incentives for building conversions, knowing that they're going to have to convert their building from either natural gas or electricity to geothermal, and really just trying to maximize the number of square feet that are already adjacent to our infrastructure, so we don't need to have more assets, more pipeline in the ground. So, you know, that's kind of our lower hanging fruit, is infilling our existing system. The next piece of growth would be expansion of our system. And again, being just in the downtown core, we are expanding. A lot of our expansion is to commercial buildings, but we also have a lot of residential kind of on the outskirts of downtown. And so we're looking at expanding both to commercial, to our residential. Recently, we extended our lines across the Boise River over to Boise State University, where we're heating now 11 buildings on Boise State's campus, and they have a lot more buildings that could be connected. So we're working closely on how to get them connected. But then also there's a whole another market of both residential and commercial south of campus. And so we're really looking at strategically, where is the best way to expand? You know, something we've learned on other projects is it's really difficult to expand without a commitment. Until we know a building wants to connect, until we know that there's actual interest in it, we really don't want to just start extending pipelines in hopes that there'll be a connection, because there could be assets and infrastructure there that we have to maintain for, you know, for 5, 10, 15 years before we start getting a return on investment. And so right now, the way our business model works is, as buildings want service, we will expand to them. It's not shown on the map here, but here on the west side, we've got a couple new buildings that are requesting service, that we're going to have to make a couple block extension to them. And this gets really tricky on how do we make that extension. A couple different ways. Number one is the cost to extend it. It's not cheap. We're looking at costs close to about $150,000 per block. And so, you know, when a building 2 blocks away wants to connect, right now they have to pay for the pipeline extension. They have to pay the $150 a block, or if this was 2 blocks away, they have to pay the $300,000 to get the pipelines to them. In turn, what we'll do is we will then give them a credit in the amount of that construction. So if they fronted $300,000 to extend this pipe, they will then have a $300,000 credit on their account, and essentially get free water until that credit's worked down, which could be a long time. but that upfront capital cost, it can be hard on new construction, on developers. So that's another piece of the growth that we're evaluating, is how to extend service to buildings without them having the burden of this upfront capital cost. The other issue that we have when we extend pipelines is the hydraulic aspect of it. You know, so being in the business of delivering hot water, we want to get the hot water from point A to point B as fast as we can. We want to keep velocities in our system high, so this water doesn't have a chance to decay or cool down by the time it reaches its end user. So going back to an example of a couple blocks west of our system, you know, ideally we want to extend large diameter pipes, so then we have the infrastructure in place for future buildings, for future growth, and so it's not limited to just the one building that requested it. Unfortunately, when we start extending bigger pipes, the velocities slow down, and it takes the water has a longer residence time before it reaches the end user. So then on the flip side of the coin, you know, you look at extending smaller diameter pipes. That way the velocities stay high, the end user has high temperatures, but then when there's another building or other growth in the area, we don't have capacity. So that's always a struggle that we have with extending these. And something that we've worked out on some of these branches, I'll call them branches that kind of extend that aren't looped, is we will put crossover valves. And basically a crossover valve is we're just bleeding a little bit of the hot water into the collection line, and just keeping the water moving ever so slightly. I mean, also looking at the end user, knowing that they're going to be billed by gallons, it's not fair for a building to turn on and then have a block or two or three of a cold water slug come into their building and cross their heat exchanger, get billed for it, and it have no benefit to them. So maintaining the velocities in this system has become very important to us and to the user. I'll give you an example, and it's not even a very long service. Where my cursor is here, this is a performing arts center on the Boise State campus, and they have about a 300-foot service line. And right after we extended that service line to them, they called and said that every time their building calls for heat, this slug of cold water comes across their heat exchanger, and it actually lowers their building loop temperature. And so they say for the first 20 minutes, it lowers their building loop temperature. For the next 20 minutes, it brings their building loop temperature back up to where it initially called for. And they don't actually start seeing heat coming into this building for about 45 minutes to an hour later after the building calls for heat. And in that entire time, they're getting charged for every gallon that's crossing their meter. So we put a crossover at the end of that service where, again, we're just bleeding just a little bit of water, you know, kind of the analogy of the shower. You know, you turn it on, you don't want to wait too long for that hot water to start coming. And we put that crossover in, and immediately, every time this building calls for heat, the hot water is there for them. And anyway, the crossover solution solved that issue, and we've replicated that in multiple places across our system, just to keep water moving so nothing sits stagnant.
Hey, John, can I ask a question while you're still here?
Absolutely.
So from the perspective of the city, is it possible to get some cooperation on zoning for density increases in the areas where you already have lines? And I don't know if that's something that the city is really interested in helping you out on.
Yeah, I mean, I'd say there's definitely possibilities for different zoning, different uses of these lots. It's already a pretty high density here downtown. You know, this is all going to shake out as part of the strategic plan that we're currently endeavoring right now. And one may be, if you're adjacent to an existing line, there might be a mandate requirement. I mean, the city of Boise has recently established some very aggressive carbon neutrality goals, where, and I'll probably get these dates wrong, but all city facilities are going to be carbon neutral by 2035, and with a goal for all of the city of Boise, all commercial and residential buildings to be carbon neutral by, I believe, 2045, if I'm not mistaken. So in the past, historically, this has been a unique system that buildings have had an option to connect onto. This is one of the only utilities in Boise that customers have options. We don't have an option on where our power comes from. We don't have an option of where our water comes from. We don't have an option of where our sanitary sewer comes from. But buildings do have an option of where their heat comes from in a building. So right now, it's been at the request of buildings to connect. And that's something that may be changing. Is it's not going to be as much of an option. There's going to be more restrictions of why you do not connect, or maybe taking it as far as a required mandate if the utility is already in front of you. Okay, so moving forward, so we take care of our existing foundation, take care of our existing customers, our existing operations. We're looking at growing our system both by infill and expansion. But then I'm going to say the capstone on here that we're also exploring very seriously is innovation, or other uses of this water. I started talking at the beginning of this presentation that there are a lot of greenhouses in the Boise area that are using this for sustainable year-round food production. There's a lot of recreation, a lot of hot springs resorts, both developed and undeveloped in the area. This low temperature water can be used for all kinds of industrial applications. And innovation on here, a feedback that I get from a lot of building owners is, wouldn't it be nice if this utility could be a combined heating and cooling district? And so that's something that we're really studying, is how could we convert this to be both a geothermal heating and cooling system, which would take a lot of the building's energy demand onto us. There's some technologies that are out there. There are some heat pumps that can be using this 170-degree water for cooling, but they're new. They're very expensive. The most common way that we're hearing is to run a third pipe along with these, running chilled water. And so then buildings have the option of the hot water, the chilled water, and then we've got our collection line. That's something that I've seen is going to pick up a lot of traction, especially with all the different technologies and successes of heating and cooling districts across the world. It's something that we're seeing a need for, and I think would be a really great use of our resource if we can pull it off. And so between that and the other innovative uses, we're really exploring how to best capture, how to best use this resource, and make sure we continue to do it responsibly, and how to manage it effectively. Technologies. So just looking at a couple of these pictures here quick. This picture in the top right corner is another application where we were using HDP pipe. This is in a historic area of downtown. And again, you can see that we got to open up an entire block of trench at the time. And this becomes really problemsome, especially when there's a lot of night activity. There could be bars and nightclubs, and these are just really heavily used areas, both day and night. One that I'm really excited about, that's been proving to be really successful, and I got lots of other maps on here, but here's just a snapshot of one of them, is we are now using infrared cameras to fly our system, and we can identify our geothermal lines very clearly. You know, this was actually brought to us by mistake. There's a gentleman here in Boise that was flying over buildings at night with an infrared camera, and he was looking at how buildings were losing heat. And you know, then he'd go approach the buildings and figure out how to tighten their envelope and make their building more efficient. And he came into Public Works one day and said, "Geez, guys, there's something going out in the streets. I don't know what it is." And he wasn't aware of our geothermal program. And he thought it was either really hot power conduits or he wasn't quite sure what was going on. So we pulled out our mapping, and it turned out that the lines that he was seeing were our geothermal lines. And we could see them very distinctly, very clearly. But something else that caught our eye was we could identify what we're calling hot spots. What you know, they kind of stick out like a sore thumb. There's something going on subsurface where, you know, historically as a utility, we were very reactive. We may have known we had a leak in our system, but didn't know where it was. And so all you could really do was sit around and wait for it to surface. And you know, for the first 30 years of this program's operation, that's the way we responded. Now we're doing this every year, and we've got a couple programs that can overlay subsequent years and identify any changes. And we're seeing, and we can see these hot spots, and so then we can schedule them. We can do a planned shutdown. We can do it on our terms. It doesn't have to be so reactive. It doesn't have to be in an emergency. We can gather the right resources, give proper notifications, and go make a repair on our system on our terms. Over the last, I'm going to say about 5 years, we've tackled about 20 of these, and it's been very successful. We've been fixing leaks on our system that there was no surface evidence that there was a leak. And I'm happy to say that as of this last summer in 2021, we have fixed our last known hotspot of our system. So just over these last 5 years, we've been taking this very, very progressive approach to looking at our system and tackling any leaks on our system prior to them surfacing, prior to them to being an emergency. It turns out that 9 out of 10 of these hotspots that we do fix are related to corrosion. And most of them are related to corrosion on our original system that was put in the 1980s. We just see this very accelerated rate of corrosion. You know, to go back to material science class, the corrosivity curve of carbon steel has this bell curve. And in the top of this bell curve is about 180 F. That's right at the temperatures of our geothermal water. And so if our water was any colder, things would corrode at a lesser rate, or if they were any hotter, things would corrode at a lesser rate. But it's, you know, fortunately we're right at that apex, and so we see corrosion happening really fast. And in fact, you know, it was identified corrosion was happening very early on in their system, and so there's been different attempts on how to prevent it. You know, originally a lot of the valves, a lot of the couplers, they were just direct bury, and the direct bury with this hot water with the soil contact, it made these steel fittings just crumble within a matter of years. So we put a lot of those in vaults to eliminate that surface metal interface. And then we started going to a lot of different stainless steel couplers. Here's an example of one service tap that we used for a period of time. And you know, this was spec to us as 3/16 stainless steel, which again, back to material science, you have a very, very minimal rate of corrosion. But this was pulled out after 1 year. And we just saw what this is referred to as stress corrosion cracking. And we actually had Boise State University do an entire material study engineering failure analysis report on why is this happening. And it turns out that it's just this perfect storm that we have. It's this temperature of water based on the corrosivity curve. It's Boise just naturally has higher corrosive soils. And you know, it really didn't matter what some of these materials were. We were seeing corrosion of them. And so that's another benefit that we're seeing with this HDPE pipe is when we need to make a new service connection, it's a plastic on plastic weld, and there are no metal fittings at those locations. Okay, moving on. So another element, another aspect that the city's really taken some aggressive measures is on education of what is geothermal, what's it used for, where does it come from, you know, tying it into some of the sustainabilities, the carbon neutrality goals that the city set. So the city owns and operates a large, we call it the Watershed Educational Center. Basically, it's everything one water. It's everything water related here in the valley. Learning about where it comes from, where it goes to, how it's treated, how it's disposed of, from drinking water to sanitary sewer, and now more recently our geothermal program. We've dedicated about a third of this entire location to geothermal education. You know, and when we started about 5 years ago with this, it was mainly targeting younger generations, you know, grade school kids. But that is now morphed into now both child and adult education, where we offer a couple programs a year, learning about not just our geothermal program, but geothermal in general. You know, what does it take to produce electricity from geothermal? What's the difference between our geothermal and ground source geothermal? We have an interactive display out there it's kind of a globe where you can look at all different uses across the world, what they're using it for, what % of their energy is offset by geothermal. This is just a really fun painting that we commissioned. There's an artist out of Britain, Joe Hill, and it's in one of those anamorphic paintings where from a certain angle, it looks like it's three-dimensional. It looks like you're kind of falling into the crevices of the earth. And you know, this is one that we then put a photo booth on, and we're seeing these pictures, I'm going to say, go viral, where kids are really excited to come get their picture taken, post it on their social media, and help portray and spread the message of geothermal use. Another one that's been really successful is we offer these bronze plaques to all buildings that are connected to our geothermal system. And these bronze plaques were originally developed for the city to help showcase the geothermal program. But we're learning, and just to get more understanding, more interest in it, but we're finding that buildings are just as excited about them, if not more, to have them, because they're seeing a whole shift in culture where they have different tenants, they have different visitors, different users that want to know that this building is using a clean energy source, that it's you know, committed to their environmental footprint. And so, you know, it may be somewhat of a marketing piece for the buildings, but it's also somewhat of a marketing piece for the city's program. So it's been very, very successful. And then also, we're also working with a couple of different artists where there's now a handful of different commissioned art pieces and sculptures that signify geothermal. This is one that was put together just a few years ago over on Boise State University's campus. And you know, the further you dig into it, the more meaning, the more messaging it has. But at a high level, you know, it's circular in nature, signifying you know, this water comes out, gets used, goes back in, and has that cyclical approach. on one side of them where they're shown hot as the hot water. There's lots of different piping and mechanics built into the art. On the cold water side, as it's going back in, there's lots of downtown streetscapes, grids, kind of signifying the utility side of it, going back and then goes back into the ground and starts the process all over again. So a big portion of our time now is also looking at public outreach and education of this program, and you know, we're always looking and trying to find new innovative ways to showcase this, and these are just an example of a couple. Okay, before I keep going, I see there's a couple questions in the chat. Carter, I don't know how to get into the chat. Can you read those off?
I can just read them to you if that's okay. There are three, I think.
Okay.
So one of them is from Mike Long. He says, different guy, not working for Boise City, but with the large downtown growth, is there any mandates to connect to the system?
Okay, great question. Currently, no. Currently, it's a choice. Currently, buildings have the choice. How do they want to heat their building? And the three most popular downtown are natural gas, electricity, and our geothermal program. But there's no requirement to connect onto it. But that's something that may change. You know, again, trying to meet these carbon neutrality goals here in Boise, we're looking for more use of this resource. We've proven that the resource is sustainable, that the program is successful. You know, a big challenge that we do have here in Boise is that we are the largest, how do I say this? We're the largest city that's separated from any other large cities. I don't think I'm saying that quite right. The next largest cities are hundreds and hundreds of miles away. So in turn, a lot of developers, a lot of the mechanical engineers who are putting the building designs together are not familiar with geothermal. Geothermal is such a niche utility that an out-of-state developer hears the word geothermal and it's new to them. And so there either has to be a high level of you know, education on how this resource is used, how inside a building mechanically it can be used, or they just kind of go back to their cut sheet and they know exactly how to design a building using natural gas. So that's something that we struggle with, is how to get in front of developers before they've already put their mechanical, electrical, plumbing plans together. And I mean, geothermal done right, it's a much simpler way to heat a building. You know, not having to have a boiler, not having to have, you know, the footprint that most mechanical rooms have for boilers and exhaust and inspection. You know, these plate and frame heat exchangers are very compact. There's no mechanical parts. If you pull the right delta T out, there could be an economic savings compared to other heating sources. And knowing that it's a local city-run utility, there's not going to be that volatility that there is in gas prices either. So we're really trying to, right now, we encourage connections of it. There's no requirement, but I wouldn't be surprised if that changes in the not too distant future.
Can I ask a question? And there's also another question in the chat, but are you the owner of the heat interface units, the plate heat exchangers? Or is the building owner? Yeah.
Great question, thank you. The buildings are responsible for their heat exchange. So we run this as a utility where we pipe the water up to your building and we stop there. Then how it's used inside of a building is on them. And Again, sometimes it's done very, very efficiently. Sometimes it's done very innovatively where they're cascading the uses. Sometimes they try to do a plug and play. They find a cheap, simple heat exchanger and plop it in. And often it works, but knowing it could be working better, could be working more efficiently for them. But no, we don't own anything inside of the buildings. We own everything out in the streets. Pump the water, take it to a building, collect the water, and then re-inject it. But what happens internally is out of our control.
Okay, John, there's another question from David. He says, have you considered rejecting heat to the domestic water lines?
We have. We have on a small scale. So one that we're playing with right now is Boise State University. Their material science program is using thermoelectrics to produce electricity off this low temperature heat. And these thermoelectrics have the potential to be doing so, but what they need is that delta T. So you need some kind of heat exchanger already. And if you just use thermoelectrics like they're intended to, you have them on a heat source, and then your delta T is atmosphere. And we're seeing that we can get more efficiencies of it if we could put a cold water stream on the other side. And so now we're looking at using these thermoelectrics for inside of buildings, where now a building could say they're heating their building with geothermal. The some or all of the electricity is from the geothermal, but then that cold water stream would be their domestic water coming into the building, and it would either be heated or preheated from the geothermal. So it's kind of more of this cascaded use of it, but also just still looking at other ways to pull energy off of this water. I mean, it kind of seems like they're at least here in the United States, if not globally, there is a big shift of going electric with everything, and a big reason why is because they can sell electricity as also being renewable. And so we're seeing a lot of buildings that are choosing to go with electric heat sources, because they can say that electricity is coming from a renewable source. And so now if they could be heating their building with geothermal, but also instead of purchasing power from the grid, they have a small unit that's generating their own power. Again, it might not be all of it, but it could be some of it. You're just getting more bang for your buck. You're getting more energy off each gallon of water that's going into a building. There's also one out there, drawn back, Electrotherm. We met with them a couple weeks ago on a small scale power generation using this water. They're not large facilities, but they can produce about a 50 kilowatt per unit. And it's something that could be put inside of each building, where we're another way to be producing electricity off of this water.
Okay, John, so we have about 5 minutes left. Do you have more material you want to cover, or should I ask a couple more questions from the chat?
I think I covered all that I really should without going down any deep rabbit holes. Why don't we see what questions you have, and then if you don't mind, feel free to pass my name out. And if anybody has any other questions after this, feel free to reach out to me.
Okay.
And I'd be happy to respond.
Okay, well, let's do at least one more then. Let's see. Sigurður asks, from a geothermal reservoir point of view, if it comes to it, can production from the current reservoir be increased in a sustainable manner to supply the whole city with hot water for heating and industry?
Okay, great question. I'm gonna switch to a different slide here. So right now, our aquifer, our reservoir here, has a moratorium on it, meaning there can be no future development of it. And that's because our aquifer is very susceptible to over pumping or over withdrawal. looking at this is a hydrograph of our geothermal aquifer, and it was more or less pretty stable until the early 1980s when these other three systems came online. I would point out though, when the city system first came online, it was a pump and dump system where we were pumping the water out of the ground, heating buildings, and then discharging this water to the nearby river. Over about 5 years, this aquifer declined about 40 feet. It made a lot of other wells go dry. A couple other districts had to drill deeper wells. And we could really, I mean, the data was there, the evidence was there that we were mining this resource. So the city then, had already spent millions of dollars, had this utility in place, wanted it to be sustainable, but this data was pointing otherwise. So in 1999, we started doing some seismic siting to drill an injection well. We drilled an injection well and completed it in 99. And then going back to this hydrograph, here was the 1983 when it dropped down. Right here is 1999. Immediately, once we started re-injecting, aquifer levels started coming back. In 2013, they exceeded pre-1983 levels. And each year, although can't see it very well here, although very small increments, this aquifer level is getting higher and higher each year, which basically says that the aquifer, this reservoir, is as healthy as it was before these geothermal systems began operation. So from a resource standpoint, we believe that we're going to be able to not only secure the water rights we have, but we'll be able to increase and get additional water rights. As far as serving all of Boise with geothermal, that's probably too far-fetched. But being able to serve more of the downtown core or more within a geographic vicinity of downtown is absolutely a possibility. Something I am watching close though is these are all the seasonal fluctuations. So our aquifer reaches a high point around September, and then between me and the other districts, the levels get drawn down, mainly from one of the other districts that's still a pump and dump district. It draws down to about February timeframe, and then it slowly recharges over the summer months, and this cycle continues. What I need to watch closer, what I am watching closely, is just making sure that the amplitude of these seasonal fluctuations don't start getting too extreme. But again, these seasonal fluctuations really aren't because of our operation. It's because of other geothermal uses here in the valley, where they're pumping the water out and not putting it back in. So anyway, I guess to make a long story short, we are getting additional water rights for it. We see the reservoir, we see this aquifer is very healthy, but we're going to make sure that we take baby steps at it. We're not going to overcommit this resource. Right now, our growth strategy is no more than additional 5 million gallons per year, just so we can always be monitoring the health of the aquifer before we're overcommitted.
Great, thanks, John. Okay, we're about out of time, but before we end, let's have everyone, if you can, turn on your cameras and let's give a round of applause for John for coming on and giving us this presentation.
Great talk, great talk.
Thank you, appreciate it. Well, again, if there was a very abbreviated version, I could almost dive into any one of these topics and we could talk for hours about it. If you have any questions or you just want to know more, or if you're ever in the Boise area and you want to swing by, I'd be happy to entertain you and keep this geothermal community, close and learning from one another.
Okay, great. Thanks, John. And if you guys want contact info for John, you could contact me or Matt or someone in the geothermal student chapter. So, but thanks again, John. We appreciate you. Good to hear from you.
Okay, no problem. Thanks, Carter.
Thank you.
Thank you.